So before I get into the big data aspects, a number of people have asked questions about how does R really work with H2O. And so I'm going to throw up a slide just as a continuation of Patrick's talk and a kind of a bridge to Arno's talk. So this diagram over here is showing how R on the left side actually integrates and communicates with H2O on the right side. And the key to understand this dynamic is the R interpreter on the left is using the H2O REST API to talk to the H2O cluster. So the cloud on the right side is a whole separate stack from the R on the left side. And you can see that what I've tried to do here is color code each of the different levels of the stack to be consistent on the left and on the right. And on the left, you can see the person is interacting using a standard R process, nothing special. He'll use the H2O package for R, write a script, and call, for example, H2O GLM, or even before this, H2O.import file. And what's key to understand here is that the work that's being done, it's all being done on the right hand of the picture. The cloud itself is doing all of the heavy lifting. And on the left side, R is just a language to tell the cloud what to do. But none of the big data ever flows through R itself. And that's a really, really important understanding. One person, I think, asked before, well, what happens if I try to take all of my big data and bring it back into R using as.data.frame? And the answer is your R session is gonna be overwhelmed. It's not gonna do any better than it would, for you today. Adding H2O isn't going to make your R faster or better on the left side, but what we do is provide this package that lets you proxy the real work to the right side, and that's what goes fast. That's where we've put a lot of energy building our Java infrastructure from the ground up to give an engine that's going to perform well for you guys. So any questions on that? I just wanted to get that in there because a lot of people seem to be asking questions about it before I move to the actual talk. Okay, great. Okay, great. So let's now start talking about H2O in big data environments. And by big data environments, I mean really where people have their data. And the outline of this talk is basically going to just spend a few moments on motivation and observations and some of the goals we have for H2O, then talk a little bit about the architecture of big data environments and how H2O works with them, and then I'll leave some time at the end for questions. So from a motivation point of view, information is the new gold. And information comes from data and tools to extract the information from the data. And that's what we're trying to do with H2O, is to give you a best-in-class tool to do that. And one of the interesting observations that I've had personally from last year at New York's Strata event to this year's, which was just last month, is last year lots of people came and talked to us and really were frenetically trying to collect data, but they didn't quite know why yet necessarily. They sort of had this idea that data was important and they needed to save it, but they weren't sure what they were going to do with it. And this year, there's a drastic change where people have a plan. They want to do fraud detection. They want to build customer intelligence models. And so reading data, building models, making predictions at scale, that's what people are wanting to do now. In terms of observations, one of the things that we've noticed, Sri likes to say, data has gravity. And what that means is it's very difficult often to move the data. So if a customer has their data on-prem in a Hadoop cluster, if they already have it in S3, if they have it somewhere else, it's often difficult to move it because there are regulatory requirements from the SEC or from the healthcare field, privacy requirements, possibly just company security policy, or sometimes just the sheer size of it makes it cumbersome to move around. So one of the goals we have is to be able to move H2O to the data. Another observation that we've had is HDFS and S3 are really, really excellent data stores. I mean, those have definitely captured a large part of the market. So we want to work in whatever environment that you've already got. That's sort of a key insight. And of course, buying new hardware, if I want to go to one of you as my customer and say, Mr. Customer, before we can start, please spend $50,000 and let's go buy a new cluster and rack it and put it in a data center, that's often tough, right? So it's much easier to say, here's a piece of software, let's just run it on the cluster you've got. Just unpack it, run it on your Hadoop cluster, and I'll show you some of the architecture slides of how that works. And then of course, finally, one of our core goals is to make H2O a best-in-class machine learning library and application that you can use in whatever environment you've got, and to interoperate nicely with other open source projects. So just, I'm going to quickly go by this slide, but the point is, what supported Hadoop environments? Let's start with talking about Hadoop. Well, we support basically all of them. Whatever you've got, it's definitely worth giving an H2O shot on it. In terms of data support formats, CSV, the row column kind of idea is how we best handle data today. We do have an SVM Lite parser as well, which is a sparse format. So if you do have some sparse data, it's possible to read that in as well. And then the folder of files approach is basically if you've got lots of CSV files in one directory, we can read in that whole directory in one shot and be able to turn it into one giant amalgamated data set in H2O's memory. And the reason that we do that, or the original reason, is to support Hive. So Hive queries result in lots of part files that show up in one big directory, and you can just point H2O at that directory of part files and slurp them all in. And then for future, we have lots of customers asking for different file formats to interoperate with. A couple of the most common ones that have been asked for are ORC, JSON, and then another one that's not even mentioned here is just standard JDBC query, to be able to read in from a database. So those are all on the roadmap. So let's talk about Hadoop a little bit more, and by Hadoop, I mean both MRV1 and MRV2. So really, our implementation isn't that different for MapReduce 1 and 2. So Yarn is fully working here. And it's really, really easy to start a cluster. Literally, this line in red that you can see here, Hadoop jar H2O driver.jar, just type in a one-liner to your shell, and it'll instantly launch a cluster on demand of the size that you asked for. So here you can see this nodes argument, nodes 3 will give you a cluster of 3 nodes, and each of those nodes will be 50 gigabytes. So very, very straightforward. In fact, I would say this is the easiest way to launch a big cluster today. Other interesting points about H2O and Hadoop, and particularly Yarn, H2O uses Hadoop's MapReduce to launch. So in order to get cluster resources, to get CPU and memory from the cluster, we have to ask the resource manager of Yarn or the job tracker of Hadoop, please give me resources. But once we get those resources, we behave very, very differently from a typical MapReduce job. So we actually don't do any real Hadoop maps and reduces. I've been told we abuse the MapReduce API in that way. It's as if you're just creating a few mapper nodes, or as many as you ask for in the command line. They all need to come up at the same time, and they form a cloud. So what you're creating is an H2O cluster within a Hadoop cluster. And I've got a picture of that I'll show in the next slide. And the point of that is all those mappers that are running, they all communicate with each other, which is a little bit weird. Normal Hadoop jobs don't do that. The mappers are generally independent. For us, we actually don't have reducers at all. Our whole point of using Hadoop is to get CPU and memory resources. So the mappers start, they claim their resources, they form an H2O cluster within your Hadoop cluster, and then you get to run H2O level jobs. In terms of config for getting things to work on a typical cluster, you generally have to tweak the settings in Yarn for you to launch a very, very large mapper. And so those, just for convenience for anybody that wanted to try this on their own, I gave you the most common settings that you need to change there. And one other question is, okay, how do I prevent H2O from taking over my whole cluster? Because I know that H2O wants to use all the CPUs and memory that it can get. And so on the memory side, whatever you launch with is what the cluster's going to take, because that's how Yarn containers work. They allocate the resources up front and prevent different jobs from affecting each other. But on the CPU side, it's a lot more dynamic. And we actually have a switch built in now that lets you limit the number of cores that H2O will use if you want to leave room over for other jobs to run as well in side by side. So here's a picture of how H2O actually deploys on Yarn. And what you see is at the top, as I mentioned before, there's this H2O jar command that you run on the command line on your gateway node that talks to the resource manager. And the resource manager then talks to the node managers in Yarn and creates as many nodes of H2O mapper tasks as we asked for. In this case, I asked for 3 in the example on the previous slide. So in our Hadoop cluster of 6 nodes, we're getting 3 H2Os. And what you'll see is once they've started up, they will form a cloud. And here, now you've got an H2O cluster, and I've actually removed those other unused Hadoop mapper or Hadoop nodes from the picture, but of course they're still there. It's just pointing out that as an H2O cluster, we're only using the subset that we asked for. Another interesting point is I did not move the HDFS guys at the bottom. So the data nodes are still going to have, wherever the data is on HDFS, of course, we're going to access it where it is. So even though some of the node, CPU and memory resources are out of play at this point, the data can still be anywhere in your cluster. And now, the next thing we do in H2O, generally as a user, is want to read in the data. And one of the really key insights here is we read in data from HDFS once, only once. And this is super important. H2O is an in-memory platform for machine learning, and you want to run iterative algorithms in memory. If in a traditional, for example, MapReduce job on Hadoop, what would happen is, between iterations, you'd be using disk in order to store results between each iteration, and you're really just doing I/O and not much CPU and memory at all. What we've done in H2O is from the ground up, design an architecture that has in memory. Memory is the center of the universe in H2O. And as you can see in the next slide, once we've read in data one time, now the iterative algorithms, the machine learning algorithms, will do an in-memory MapReduce. And this is an H2O, a pure H2O MapReduce, where you start reading data from memory, you perform your iterative algorithm like GLM or random forest or whatever, and then you write the results back to memory. So we never want to touch disk at this point. If you're touching disk here, it's not the experience you're looking for. So the goal is to have your data fit in memory, to have the algorithms run in memory, to give you speed and to give you, to scale that way. Any questions at this point? Yeah, question.
Once the data is read into memory, is it immutable, or it can be changed, or it has to be reloaded all at once?
Right. So the question is, once the data is read into memory, is it mutable or not? And the answer is yes, it is mutable. So in fact, one of the things that's very interesting about the data science field and about people using R is that they're constantly changing their columns. They're constantly munging things. They're constantly adding columns or removing columns, or creating expressions with groups of columns and wanting to add it. And so one of the other very interesting insights about R versus H2O is that in H2O, to create a column, to delete a column, it's cheap. So I know I'm not an R expert. We have R experts that could to talk about this maybe better than I can, but my understanding is that in R, when you actually do a modification, it makes a copy of the whole data set, which is extremely expensive. What we do is we actually, underneath the hood, don't do that. You know, the H2O engine itself optimizes these operations for you. And so if you just want to add a column, it's cheap. If you want to delete a column, it's cheap. And that's very, very intentional, because it enables you to do things with big data that you otherwise couldn't do. Other question? Yes.
What if the data that you have stored in HDFS would not fit in memory in the three nodes that you have in your cluster? Then is there some kind of intelligent switching between the traditional store some intermediate results on disk type of strategy, or? Yeah,
good question. And this is a popular question. If the data is too large to fit in memory, then we do have architected in the system a backing to disk approach. But what I'll say is, if you're doing that, that's not the experience you were looking for, right? Because instantly, the whole point of doing stuff in memory is to be fast. And as soon as you're doing that, you're losing really that advantage.
I see. Second question. So say that all the data can fit in memory, but some of the intermediate calculations of your algorithm explode and no longer fit in memory. So for example, if you have n observations and p features, and you want to calculate a n by n distance matrix, if n is really large, then that n by n matrix is dense and really, really big.
Yeah, that can happen. And so what we try to do is in the architecture to be as tolerant of that sort of thing as we can. And we're constantly wanting to add more checks to more places that prevent you as the user from kind of falling over by doing something that you shouldn't have been allowed to do. But definitely, there's room to improve there. H2O is still a fairly young product, and we're constantly improving it all the time. So one of the things that I think would stand to benefit from improvement is exactly that. It's to do more, I'll use the word admission control of operations, to give you some feedback if you're going to get into trouble. And that's an area for future improvement. We have some, but it could definitely be better. More questions? Yeah, the gentleman here.
So apologies if you said this, but I wanted to clarify on your mutable data.
Yeah.
You mentioned columns a lot. How about insertions of rows? Is that also fast or optimized?
Insertions of rows, we actually don't support today.
Okay.
But we could do that. We just haven't done it. It's basically a case of appending additional data to the end of the data set. And if you were here for Cliff's talk in the morning, I'm sure he talked about how the data was striped around the cluster. And so it's striped around in groups of rows that we call chunks. And so it wouldn't be hard to create the equivalent of an R-bind operation for our users. We don't support that today. We could. We do support C-bind. So if you have two data sets that have the same height, the same number of rows, you can C-bind them together. That's fairly expensive because it does have to do a copy there of one of them. But R-bind is a future roadmap thing. We just haven't done it yet.
So say instead of appending a row, I wanted to alter the data within a row.
Yeah.
Because it's broken up into these small chunks, I assume that's actually quite efficient as well.
It's efficient if you do it. Well, yes. So that can be done efficiently. Yeah.
Okay.
Now, whether I'm just trying to think off the top of my head here whether we can actually support that from R, I'm not sure. But certainly, if one were at the Java API, and we could certainly do it from R if it's not available, that type of thing is definitely possible.
The reason I bring it up, I just live in a world where we constantly get new data.
Yeah.
And rather than rebuild the whole thing, it would be great to just append the thing or update information. We get new information on a particular
that makes a lot of sense. I mean, to date, most of the use cases around that sort of thing have been around columns, so we've focused there. But rows would certainly be possible.
Okay, thank you.
Yeah. Sure.
What do you recommend is a reasonable balance between cores, amount of memory, and amount of networking resource?
More and more and more.
Well, yeah, but you've got a fixed budget, right? So you need, need to balance it. And it's probably quite different from Hadoop.
The different algorithms actually make quite a bit difference for what you just asked there, actually. So some algorithms perform really well with as many cores as you can possibly give it, like deep learning. Deep learning, and even GLM, they'll parallelize very well. Some algorithms, like the tree algorithms, will do better if you give a larger node with lots of memory and maybe not as many of them, because if you have too many, then you'll be bottlenecked by network as opposed to by CPU. So it sort of depends on what your data looks like and what workload you're trying to run. But in general, what we've seen is that the thing that will run out first, if you have lots and lots of data, tends to be memory. And if you lesser data, it'll probably be CPU. And I/O is usually not the thing that will bottleneck you in H2O, especially if you run, for example, GLM. GLM does an excellent job of partitioning the work to different nodes without needing to do a lot of communication. But if you've got a big random forest with a huge depth of trees, it's going to have to send data around, and there's really no way around that. Next question? Yeah.
Yeah, I think you said a few minutes ago that R copies the entire data set if you add a column or change something in it. But it doesn't actually do that anymore. It shallow copies each column.
Okay.
So
Well,
that
thank you
problem's been fixed.
for correcting me.
Okay.
Okay. Let me move to the next slide
We
here.
have one more.
Oh, one more question?
Sorry,
Yeah.
quick question on the HDFS side.
Yeah.
So do you find that people using H2O don't tend to be doing other MapReduce, Pig, Hive stuff on the side? And the reason I ask that is, since you're reading it once, you don't need the replication factor of 3 or more in HDFS. And since hardware is really expensive, if you read it once and I leave just a replication factor of 1, maybe.
Well, that's an interesting question. That's a good question. So our experience is that people still want the replication factor of 3 because their data, they don't want to lose it, right? The part of the replication factor of 3, in addition to making extra copies that allow ingestion to be more performant, is to make sure that you don't lose data when one of the nodes dies, right? And so I haven't had anybody reduce their replication factor other than as an experiment.
Well, where I was going really was, the operational costs of running 3 sets of hardware underneath are really expensive as well. So, if you turn off 2 of them, right, your data center is now using 1/3 of the energy that it was using before. So I was just curious if people have actually gone to that level with this, or are they leaving everything running, run H2O on parts of it, and then keep running MapReduce, Spark, whatever they're running on the other side?
Right, I see. Well, what we've had people ask about and try out is, having dedicated, scheduler partitions for H2O, so you can always start an H2O cluster, but still be able to run, cluster saturating MapReduce jobs on the side. I would say the thing to be more careful of is to just leave some resources left over, because when H2O wants to start, as I've shown in the picture, all the nodes of H2O need to start at the same time, or you don't get a cluster, right? So that's an important, from a resource mindset of using H2O, that's probably the one that you've got to be aware of when you're in this kind of a shared Hadoop environment. Does that answer the question? Okay. Yeah. Actually, the microphone's coming.
Can we have dedicated nodes just for H2O, like in Hadoop cluster?
That's up to you.
No, is there any setting where we can say, okay, I have 30 nodes, but I only want these 3 nodes to deploy H2O?
Okay, got it. So H2O is a very, very simple job. But one of the things that I can tell you is it's a derivative of the tool runner framework. So, which is kind of the oldest framework that exists. So if you want to pass in -D options that the resource manager can work with to decide where to place things, that's certainly something that you can configure on your own. It's not something that the software needs to really do anything to support. Okay, so let me move to the next slide. And now that we've talked about Hadoop, let's talk a little about Spark. And Spark is of course, very, very popular in-memory framework. And as H2O people, we want H2O to run as an application on top of Spark and to be a library that people that are interested in Spark to be able to work with and even interoperate with MLlib, which is one of the machine learning platforms available for Spark. And the way that we've done that is by creating an H2O RDD and allowing you from a single Scala program to be able to control both Spark and H2O aspects in a single flow of control. So one single Scala program could, for example, and if you want to see an example of this, we can certainly show you one offline. If you go visit Mikal, he'll be happy to show you one. One single Scala program can run a Spark SQL query, pull a data set into a regular Spark RDD, and then move that data over to H2O into an H2O RDD, and then be able to run deep learning from H2O or GLM, like Patrick showed you. Those, really anything that you want to do. And then with another single line of Scala code to move that H2O RDD back into a pure Spark RDD, and to do all of this very, very seamlessly. So you don't even need to think about it. Yeah. Let me answer that on the next slide, because I've got a picture showing the data representation. So this is just the startup of how one would start the sparkling water application on your Spark cluster. Sparkling water, as some of you probably know, is the name that we've given to this combined, this methodology of bringing H2O to Spark and to have them both working interoperably for you as the customer. And really the workflow is very straightforward. It's basically just using the standard Spark submit to start a job on the Spark master. The master will then distribute the job to the different workers, and each worker will start an executor. And what's interesting about this, and this might even be more technical from a Spark workflow than most people are familiar with, but the thing that I want to point out that's really interesting and important about this is on the right side here, every JVM has both a Spark personality and an H2O personality within the same JVM process. And that's what makes it really, really seamless and from a user point of view, nice for you guys to work with. And again, once all of the different nodes on the right have come up, they form a cluster, an H2O cluster within your Spark cluster, possibly even within a Yarn cluster. So now we've got layering of clusters. And they're all accessible. The H2O nodes are now running. They're fully accessible using the standard web interface that you guys have seen already. They're accessible through R. They're accessible through Scala, of course, because after this cluster comes up, the first thing you're generally going to want to do is run a Scala program on it. This is the data question that I think the gentleman had asked. And basically what you see here is a picture showing the data source on the left, and then on the right, the same sparkling water cluster that we just created in the last slide. But what's interesting about this is now the data, it does have to, if you're moving data from the Spark world to the H2O world, you do have to make a copy, but that copy is generally very, very nicely compressed on the H2O side. This morning's talk from Cliff certainly talked about columnar compression and how we do a very nice job of making the data stored in memory, and we take advantage of that here. And then just to reiterate, from the left side, the red blocks to the green blocks, to go in either direction, it's very simple. Just a single line of Scala code, and you just move the whole thing over. And since the data is sitting in the same JVM, it's very fast, right? You've got, there's not a lot of motion across the network. Yeah, question.
Since H2O and Spark share the same JVM, why do you have to do a data copy?
The reason is because in order to get H2O to actually use the data for the model building purposes, it needs to live in the key value store. This is kind of a low-level answer. It needs to live in the H2O key value store that's distributed across the H2O cluster personality. The H2O algorithms rely on that layout of data. And so it's possible in the future that we might even have a better integration than this. Actually, our first integration of sparkling water had a tachyon in the middle, an entire third copy, and this is a dramatic improvement over that. And I think over time, you might even see better than this. But today, this is what we've gotten. And then just one more time, if anybody's interested in seeing an example of this working, go visit Mikal. He'll be available in one of the rooms on the left, on my left here. And here are some more links to various training and blog information about sparkling water. And finally, let's talk about EC2. EC2 is of course, quite different from the prior two environments. Generally, for Hadoop or for Spark, they're often, most of the time, going to be on-premise. EC2, of course, is not. And so now you've got a little bit of a different environment to work with. So some of the nuts and bolts, in order for H2O to work, let me just advance the slide here, because it probably makes more sense looking at the picture. For the H2Os to talk to each other, basically you've got to set up a security model in EC2 that allows them to communicate. So there are a couple of ports you need to open up. The details are in the slide. The other thing you need to open up or have a way of locking down is for the user to access the H2Os themselves. So each of these H2O instances has an embedded web server that is the same web server you've been playing with and the same one that R talks to over the REST API. And so really, when you're working with EC2, you need a way for the top user to interface with the cloud, and then you need to enable the cloud nodes to talk with each other widthwise. The last thing that I think is very interesting for somebody that wanted to try this is the data, of course, is almost certainly going to live in S3 if you're doing this kind of a layout. And S3 is a great choice. We run, as Sri showed you, our nightly tests are running nightly in S3. It's a nice environment. It scales very well. All of our software is distributed from S3, so we're fans of Amazon. We run lots of workloads there. Let me just go back once more and see if I have a couple of other points here. OK. So this is kind of obvious, but enough people have run into this problem that I think it's worth pointing out. Use instances that have some horsepower. So if you're running H2O, give it an instance with a decent amount of cores in memory. If you end up with instances, or even a cluster of instances, I've seen people start up and it's got less power than my laptop, right? So if you want to run on a bigger data set, I definitely suggest you give some bigger instances to run with. And then the last point, this is actually one of the trickier points of EC2, is you've got to organize your cloud so that every node can talk to every other node, and that means they've got to find each other. And so in the EC2 world, that generally means you want to copy what we call a flat file, which has the IP and port of every machine in your cluster to every node, so that everybody can find everybody else, and it's just part of the startup process. Question? Yeah. The question is, does running in a VPC help with this case? It doesn't help, it doesn't hurt. I mean, it's fine. People certainly do it. I've done it myself. There's no reason not to do it other than, the best reason to run in a VPC, I would say, is just because you're wanting more security. I mean, the tricky thing about things like Amazon and environments like that is, the more security you add, the tougher it is to work with the environment. So it's one of those either or things. You've got to choose ease of use or choose security. They generally, automation is great, right? Once you kind of have figured out what kind of environment you want, then automate it and be done, and it'll still be easy. And then just one last comment. A couple of other environments that we have heard rumors of people working with, but we haven't ourselves, so I don't want to say that we've tested them, but I've heard that they've worked, are the Google Compute Engine and Microsoft Azure. The the point here is that H2O is just a Java process. It's not special. It doesn't need to run as root. Doesn't matter what kind of operating system. Just run Java, H2O runs, and you've got a cluster. And if there are any last questions, I'd be happy to take them. Otherwise, I'll hand it back off to the next speaker. Yes, question.
Do you have recommendations on best practices for setting up multi-tenant environments? Let's say I have 200 or 300 modelers that want to use a system, and you know, they might each have their own data sets and don't want access to the other people's data sets and things like that.
Yeah, so today, in the current version of H2O, that's not supported. So in working with customers, generally the things that we do are the things that many people ask for and push us to do. So far, they've been pushing us to build better modeling algorithms that run faster, run at scale. So we have put, I would say, a lesson of an emphasis on that kind of thing. I expect that in the future, we'll do more of that. Today's product, best practices. So let me give you an example of what one customer does that's worked very well for them, actually. So their shared environment is their big data Hadoop environment, but each of the data scientists will start their own cloud and import data into their own cloud because the clouds are so easy to start and they're convenient to take down, and reading in data is pretty fast. Modeling is very fast. So people will treat the clouds as almost disposable in many instances, many cases, especially in the Hadoop or the Spark environment, where just creating it is literally one command line. And then there's, once you move to that sort of a way of looking at the world, some of these problems are not as acute. So that's the approach that we've generally emphasized so far, but I think in time we will definitely invest more in things like multi-tenancy. More questions? All right, thank you very much.